Hello, Ryan. Hello, Eric. Hello, Ryan.
Hello, Eric. Hello, Daddy.
Hello. You should say hello, teacher.
Hello, teacher. Hello, Mr. Teacher.
Yes, good job. Okay, so remember yesterday we talked about binary search tree to search your value in a binary search tree. Am I right?
Yeah.
So can you tell me what's the binary search tree?
It's like a tree with numbers.
Yeah, exactly.
But
Tree
it's
numbers.
in circles. And there's parents and leaves and roots.
Okay, so 1,
The top
0,
number is the root. Keep
2.
neat.
3. Is this the binary search tree?
Yeah.
Yes. So today our job is to validate a tree if it's a binary search tree. So we call it validate, the equivalent to validate binary search tree. So given a tree, we have to to check if it's a valid binary search tree. A binary search tree is the first of all is a binary tree, right? So
Yeah.
the binary search tree, it has to be a binary tree.
Yeah.
What's binary?
2.
Yeah, well done. Binary 2.
Yeah.
Two kids, left or right. The second one, binary search tree. The empty tree is also a valid binary search tree. Okay. The third one, the important thing.
But what about this? Just one number.
It's a binary search tree. It's a binary tree. It's also a binary search tree because it's valid, right? Yeah. It's a binary tree. Tick. This is okay. And also the third rule, very important, which is the root value has to be bigger than the left.
Yeah. Did you do
And
that
then-
for a mistake?
No. This is one node is a valid binary tree and binary search tree. And the root has to smaller than what?
The right.
The right, yes. Okay, so is this a binary search tree?
No.
Why?
Because this is bigger than the root.
That's right. Okay. Remember yesterday we talked about search a node in binary search tree. Yeah? If it's a binary search tree like 1, 0, 2, 3, and then let's minus 1, and then maybe
1.
no, it can't be 1. Can it be 2?
No.
No, because look, this is smaller than 1. But this is bigger than 1. So this can only be like 0.5. Got it? Because 0.5 bigger than 0, smaller than 1. Got it? So if we want to locate 0.5, is it smaller than 1?
Yes.
So go left or right.
Left.
Is it smaller than 0?
No.
So go right or get left.
Right.
Yeah, okay, we found it. So the complexity is what?
O log n.
Yeah, because n is the number of the nodes in the tree, and on average, if it's this the highly balanced. What I mean highly balanced is that the difference, the maximum difference between any left tree or right tree is at most 1. Okay. Is this a valid binary tree? Is this a valid binary search tree? Yes.
Yes.
Is this a highly balanced binary search tree?
No.
No, because look, the difference is this is the right node is there's no right node, but there are 2, so the difference is more than 1. So okay, this is not. Okay, so now we given a tree, we want to find out if it's a binary search tree. So we can do it this way. If we define a window like a minimum and maximum, right? Yeah, if we know this minimum and maximum, right? And if a tree if a node value has the value outside this window, then we know it's invalid, right?
But you can't see the window.
Yeah, the window, the maximum, the minimum. At the beginning, we just pass infinity, the minimum infinity and the maximum infinity. Yeah, very, very big number, very, very small number. Okay, and then when we go look, this is 1, this is I don't know, this is something, yeah, and this is something. Okay, so the beginning is minus infinity, and then bigger than infinity. So if we go left, so all the values in the left-hand tree, we have no values smaller than 1, right? Yeah? That means the right window is 1. Am I right? Am I right? The left window is still infinity. Am I right? Yeah? If you go left, we update the right, the upper bound. Because it can't have values more than 1. Yeah? If we go to the right, what should we do?
Infinity.
The small bound is 1, right?
Yeah.
Because it can't have values smaller than 1, alright?
Yeah.
So it's 1 and infinity, alright?
Yeah.
So every time we update the min and max, and then we check, we recursively, remember the recursion? Yeah? Calling itself in the lesson 1, right? Calling itself recursively update the value, to update the windows, and to check if it's a valid binary search tree. Okay, so let's do the coding. It will be quick, okay? You can tell me, okay? You can tell me what to write. So first of all, what
It's
should I write?
5 minutes already.
Yeah, I know. So what should we write now?
That.
Well done. And what's next? Define.
Binary.
Check BST. Let's call it. And it takes
Bracket.
root of the tree, and then let's call it min, and let's call it max. Okay, min and max.
Column.
Yeah, well done. So we need to check the base cases. If the root is empty, what should we do? Can you tell me what to do?
Return true.
If root is none, okay? Or you can simply write if not root, it's the same thing. If not root, or if root is none, it's the same thing. Return what?
True.
Yes.
Yeah.
Be confident, yeah, return true. Not return true, return true, okay? Got it?
Return true.
Okay, now we need to check the value if it's inside the range, right?
Return true.
Anyway, look, if root
Ow.
dot value, if it's smaller than min, or root dot value, if it's bigger than max, column, what should we return?
Return. False.
False, yeah, because it's outside the window, then it's not value, right?
Yeah, babe.
Okay, and then we need to recursively check the left node and then the right nodes, right? Remember we talked about check the left node and the right.
That looks like an apple.
Yeah, left 0 and 2. Okay, so remember what do we check? Return, yeah?
Yes.
Check BST, check BST.
You spell return wrong. It's not R-E-T-N.
ITU, okay,
It's return.
ITURN. ITURN, yeah. Check BST.
Return.
Root or left. Okay, tell me what's the next 2 parameters.
Read all right.
No. It takes the min and max. What's the min? What's the max for the root of what's the left tree?
Oh, minimum is
Min
minus,
and maximum
minus
is
infinity.
no. Min is this min, and the right value will be the root of value, right?
Yeah.
Because it can't be bigger than the root, right? Yeah. And then again, and check BST root dot right, right?
Yeah.
And what's the min? What's the max?
Max
So what's the min?
of the right.
Yeah, right hand side. What possible smallest number can?
1.
Yeah, 1, which is root of value, right?
Yeah.
And what's the least? What's the maximum?
Max.
Max. Yes, well done. So do you get it now? It is clear. Yeah.
Yeah.
This bit is check if the root. So you call itself to check until either if it's empty, then we return true. Or if it's not inside the range, right? Because it's smaller or it's bigger, then it's not in the range. We return the false, right? Why can we do that? Because a valid binary search tree, the left binary search tree and the right binary tree is also binary search tree, right? In order for the entire tree is a BST. The left has to be a BST and the right has to be a ST. So this is
BST.
binary search tree. Look. Why is this is very simple recursion. Look, if the node is a simple, if it's nothing, if it's empty, it's a binary search tree, right? if the value is not inside the range, it's not a binary search tree. Also, in order for this to be a binary search tree, the left tree has to be a binary search tree, and the right tree has to be the binary search tree. Am I right? What the complexity of this algorithm? What's the
O
what? O what?
N.
O-N, yes. Remember O-N? O-N. Why is it O-N? Can you tell me?
Because it needs the numbers.
Because
you need to check all the numbers.
yeah, exactly. Because in order to verify if a tree is a binary search tree, we have to check every node, right? If you miss one node, you can't be sure that it's a binary search tree, right? Yeah. Okay, so can you tell me why yesterday we are searching for a node in a binary search tree? The complexity is
O log N.
O log n, yes. Why is it O log n?
Because you just need to find the node.
Yeah, for example, if it's 1, this is 0, this is -1. If I want to find -1,
You go down. You
I
don't need to check that one.
yeah, I don't need to check the right hand tree. Yeah, well done. Good job today, Eric, Ryan. Okay, good job. Laughing. Ryan.
Whoa!
Okay, good job
Yeah.
today.